discussion about the deep neural networks. We will be seeing about the architecture, the various optimization techniques, the regularization methodologies that is available, and what are the various causes, solutions available for overfitting and underfitting mechanisms in this lecture. So, for today's agenda, we have the comparison between shallow and deep neural networks. We have the optimization techniques, different regularization methodologies, and overfitting and underfitting discussion. First of all, we have to understand what is deep neural networks. Deep neural networks are nothing but the artificial neural networks that will consist of multiple hidden layers. Then we will go for the difference between shallow as well as deep neural networks, and where we can apply these neural networks that we will be seeing. So, unlike shallow networks, what is shallow network means? It will consist of only one or two layers. Okay, the deep neural networks, it can consist of dozens or even hundreds of layers. So, this depth is allowing the deep neural networks to learn the complex relationships in data, making them particularly effective for tasks like image recognition, natural language processing, speech recognition and all. We can utilize the deep neural networks. When you go for shallow networks means, what will happen? It will consist of only one input layer, one hidden layer and one output layer. They are capable of learning only simple patterns. Okay, they struggle more when it comes to complex tasks. For example, a shallow network might successfully classify one linearly separable data. Okay, whereas it might fail when it is faced with intricate patterns like those patterns that is found in images or audio signals and all that. Okay. When you come to deep neural networks, on the other hand, we will be consisting of millions of input layers, hidden layers and output layers. Here what will happen means, in the input layer will receive the raw data, multiple layers of hidden layers will process those input and then which is connected using the weighted connections and activation functions, and it will produce a final prediction or classification. This we have to understand in deep neural networks. This is the comparison between shallow networks as well as the deep networks. And then we have this optimization techniques. When you train a deep neural network, it involves optimizing the weights in order to minimize the error in predictions. What and all error will occur in the predictions, that will be minimized. So, several optimization techniques can enhance the training process, like for example, we have learning rate schedules. Okay, and then we have in that itself we have step decay, exponential decay, cyclic rates and all that. And then we have momentum, RMS prop and ADAM. So, these techniques are coming under the optimization techniques. So, first, step decay. Step decay, what it will do means, it will reduce the learning rate by a factor for every epoch. Okay, so that is what is step decay is all about. When it comes to exponential decay, it will decrease the learning rate exponentially over time. And then when it comes to cyclic rate, it will vary the learning rate between minimum and maximum value throughout the entire period of time during the training phase. And then by adapting the learning rate, these schedules are helping to converge the speed and the model performance. And then we have the momentum, and then we have the RMS prop and ADAM equations. So, here we have to understand that momentum is one optimization technique that is helping the accelerate gradient descent by considering previous gradients. Okay, this particular equation, in this equation we can see that Vt is equal to beta Vt minus 1 plus 1 minus beta del j theta. Here Vt is velocity, beta is momentum which can be set between 0.5 and 0.9, and then del j theta is the gradient of the cost function. Okay, and then next when you go to RMS prop, what is happening? RMS prop is nothing but it is the root mean square propagation. Short form for root mean square propagation is RMS prop. Okay, this is one adaptive learning rate methodology only. So what it will do means it will adjust the learning rate for every parameter on the basis of the recent gradient value. So the equations can be found over here. Here gt is the gradient at time t, vt is the exponentially decaying average of squared gradients, and eta is the learning rate. Epsilon is the constant value that is needed for stability. Okay, so what RMS prop technique will do means it will stabilize the gradient values. And then next we have the adaptive moment estimation, which is nothing but ADAM. So ADAM, what it will do means it will combine both the momentum as well as RMS prop ideas. Okay, here what it will do means it will maintain two moving averages for each parameter, one for gradients which is similar to momentum, another for squared gradient, one for normal gradient, second one for squared gradient. Here squared gradient is nothing but it is similar to RMS prop. Okay, so in momentum methodology, gradient will be taken into account. In RMS methodology, squared gradient will be taken into account. Combining these two, we will get the ADAM. So here we have a rule called as update rule. So the update rule is nothing but the equations that is given here for MT, VT, MT cap, VT cap and theta. Okay. So theta value can be found out in methodology similar to RMS prop. Okay, combining both of the equations, we will be getting the ADAM equations. So when you talk about ADAM, it has become one of the most popular optimization algorithm because of its efficiency across various tasks. Moving on to regularization techniques. Regularization techniques, they are needed for preventing the overfitting in deep neural networks. So why overfitting methodology occurs means when a model learns noise in the training data rather than understanding the patterns from it at that particular period of time, overfitting might occur. So the regularization methodologies like L1 and L2 regularization technique will help to overcome the overfitting issue. So here we have L1 regularization, which is going to add a penalty value which is equal to the absolute value of the weights. And then L2 regularization is going to add a penalty value equal to the square of the weights. We have to understand this symbol is representing L1 and L2 norm. So norm is nothing but when you find out the magnitude or length of a particular vector, you have to go for L2 norm. Okay, so we have to understand the equation. In this particular equation, we have L0, which is the original loss function. W is representing the weights. Lambda is representing the hyperparameter that is going to control the regularization strength. And then we have L2 regularization, which is going to distribute weight more evenly across the features. L1 regularization can lead to sparse models with some weights driven to 0. Okay, so these are the explanation about the regularization techniques. Here we have another topic called as dropout. So what dropout is doing means it is a powerful technique. Okay, so it is going to allow for random selection of neurons which are ignored during the training. Okay, so this prevents the neurons from co-adapting too much, and it encourages the allowing of redundancy that is occurring during the representation of various features. So we have to understand one thing. During training, each neuron will have a probability P of getting dropped out, which means of getting avoided. Okay, so we have another phase called as inference phase. One is training phase, another one is inference phase. So during inference phase, what will happen means all the neurons will be used, but they might be scaled by their dropout probability. So this technique is effectively reducing overfitting while maintaining the performance of the model. Okay. Next we have batch normalization. So batch normalization is normalizing the activations within every mini batch. Mini batch means layer by layer we are doing it. So during the training we are taking into account batch normalization. It standardizes the inputs to each layer by adjusting the mean and the variance of the values. Here we have x cap and x which is equal to x minus e of x divided by var of x plus epsilon whole root. E of x is nothing but the mean, var of x is the variance which is going to computed over the mini batches, and the normalization is speeding up the training by reducing the internal covariate shift. What it will do means it will allow for higher learning rates without making any risk in the divergence and all that. Next, coming to overfitting and underfitting causes and solutions. We have to understand that overfitting and underfitting is needed in a crucial amount for developing effective deep learning models. So when you discuss about first, let us see what is overfitting, what are the causes of it, and what are the various solutions for it, that we can understand now. So first, overfitting. So overfitting occurs when a model learns too much from the training data and it captures noise instead of the needed patterns. There will be high accuracy on training data but poor performance on the validation or the test data set. Okay. So the causes will be excessive model complexity, which is relative to the data size, and then insufficient amount of training data, and there will not be any regularization techniques and all that. So in these three cases we can understand that overfitting might occur. Then what can be the solution for this? The solutions can be we have to implement L1, L2 regularization or dropout mechanism, which we discussed earlier, and data augmentation. What is data augmentation? Increasing the data set by applying the transformations like rotation or flipping of the images and all that are there, no? So we can go for data augmentation methodologies. And then we have early stopping. Early stopping is nothing but monitoring the validation loss during training. Whenever we need to stop, we have to stop when it begins in order to increase the model despite of continuous improvement in the training loss. Then we have underfitting. Underfitting, when it will happen means when a model fails to capture the underlying trends in the data because of the excessive simplicity or inadequate training in the during the occurrence. So what will happen here means there will be very poor performance during both the training as well as the validation data sets. Then what will be the causes? Very simple architecture of the model, very insufficient training epochs or iterations at that particular period of time and all that, we can say that underfitting might happen. So what will be the solutions for it? There are different solutions for underfitting. So first one is to increase the complexity of the model. So we have to use lot of architectures and a lot of layers per architecture are needed. Okay, and then we have to go for feature engineering. What does mean by feature engineering? Means improvising the input features through transformations or even going for additional relevant features. And then we have increasing the training time, so allowing for more epochs for complex data sets. We need not go for more epochs for lesser amount of data sets. When you have lesser amount of data set, you can go for lesser epochs, but here since there are complex data sets that are available, we can go for increasing the epochs. So at that particular time also we can avoid underfitting. And to conclude, we can understand that deep neural networks are representing a significant advancement in the machine learning capabilities. This enables the systems to learn from vast amount of unstructured data effectively. We saw various optimization techniques like ADAM, RMS prop, and we saw about regularization methods like dropout, batch normalization, and then we saw what can be done to overcome the challenges like overfitting and underfitting. Okay, so those who are practicing deep neural networks for various applications ranging from image recognition to natural language processing, we can think of all these techniques in mind, and then we have to make a model to predict the output. So as we continue to explore this field, it is essential to stay updated with the emerging techniques and the best practices that are available in order to ensure that the model is robust in nature. Okay, so when you go for a model, what will happen means there might be common pitfalls in the workflow of the machine learning model or the deep learning model. So in order to overcome the pitfalls, what we have to do means we have to stay updated on the techniques that are available in the current technologies, and we have to make our model in a robust manner. That is more important. Okay, so we have to have that in mind. So with that, we come to an end of this session. In the later sessions, we can explore much in detail about the various other techniques that are available in this deep learning lecture series. Thank you.